All right, thank you. So the title of the talk is Migrating and Grafting Routers. Do you want that's on? Migrating and grafting routers to accommodate change. And this is joint work with Jen Rexford at Princeton, a couple other students, and Jacobus Bannerman at AT&T. So the motivation for this work is that networks need to be highly reliable in order to avoid service disruption. At the same time, operators need to deal with change. They need to install, maintain, upgrade equipment. They need to deploy new services. But change causes disruption. So this forces a trade-off, where you weigh the benefits of the change against the disruption that it will cause. So we're presenting migration and grafting, which enable operators to make the changes without the disruption. To understand where the disruption comes from, we're going to focus on two primitive operations that operators need to be able to shut down a router and move links. So shutting down a router, first consider how a router is propagated. So on the right-hand side, you got some destination, and the route is distributed and propagated throughout the network until you reach some steady state where every router has some calculation, some path to that destination. So now when some router C goes down, the neighboring routers detect that the router is down or are told that it's going down. Then they have to choose a new best route that's available. In the case of B, there is no route available, and so it's out of luck. It can't reach its destination. In the case of A, it would be able to go through the bottom router, through a router route. It would propagate updates saying that it changed its path. And this is, in BGP, it causes a convergence event where the path propagates throughout the network, and then there's a lot of transients there, where there's potentials for loops and inconsistencies. So in the best case, it's the time that it takes to settle on this new path, which can be measured in seconds. In the worst case, as in router B, it's you have to wait for the router to be back. And in both cases, there's a lot of updates being propagated. Now, in terms of moving a link, how is it done today? Well, let's say moving this link between D and E to be between G and E. And I'll go through examples of why we want to do each of these in a couple of slides. So both D and E would need to be reconfigured to say they're no longer going to be pairing with each other. You remove the link, which would cause D to now say that it can't reach any destinations that they went through E. You would add the link, configure the routers, it would form a new BGP session, and the routes would get propagated. And so, similar to taking a router down, best case, time to settle on a new path. Worst case, waiting for the link to be up. So, like I said, that this causes the operator to have to weigh the benefit of change against the amount of disruption it costs, whether it's actual downtime or the effort the operator has to go through to avoid that disruption. So now we'll go through a few examples. For shutting down a router, one thing you need to be able to do is plan maintenance. And so you would shut down a router to, for example, replace a power supply or upgrade to a new model router. And so this is unavoidable, so operators readily do it. But now let's consider power savings. Traffic through a network follows peaks and troughs, and they can be quite significant, the differences. But you have to provision your network for the peaks, obviously. And
you're thinking of in time or over
time,
routers?
Well, over time, typically, like the diurnal pattern, when people go to work, and that's more what I was referring to. And so what you'd, possibly be able to do is to shut down some of the routers because you don't need to be able to handle all of that. But consider what would happen if you shut down this router that the red arrow is pointing at. So this isn't something that's done today because of the disruption that it would cause. Now, in terms of movement of link, so when a customer signs up for service within ISP. It lists out its requirements, the bandwidth it requires, the features it requires. And, in the ISP's network, they have various model routers and that have different features. And it picks one that meets all of the customer's requirements. Now, if at some point in the future, the customer changes its requirements, for example, requesting a new, new monitoring capability or new quality of service capability, and this router doesn't support it, the customer, the ISP, has to rehome the customer to a router that does actually support it. So this is unavoidable. The customer requested it, so of course the operator is going to do it. But they would like to be able to do it without, telling the customer, well, we can do it, but it'll take a couple minutes of downtime. Now, let's consider traffic management. So the typical way you do traffic engineering today is you have a bunch of monitoring throughout your network, and you notice that there's some congested link. So you look at what all the traffic patterns are, and you tweak your routing protocol parameters to make some of the traffic flow around that link and make it uncongested. So what if instead we can notice that this one particular customer goes out, sends a lot of traffic that goes out this particular egress point, and we can rehome that customer such that it has the same effect of taking that traffic and not going through that link. But this gives us an extra degree of freedom that we can change the traffic matrix in addition to tweaking the routing protocol parameters. And this isn't something that's done today because of the disruption and the cost. So then the question is, why is change so hard? So we argue that the root cause is the monolithic view of a router, that the hardware, software, and links are all viewed as one entity. So we're going to revisit this design to make dealing with change easier. And we have two goals in particular. The first is that routing and forwarding should not be disrupted. And by this, we mean the data packets are not to be dropped, routing protocol adjacencies should not go down, and all route announcements are to be received. And the second goal is that the change should be transparent. So the neighboring routers and operators should not be involved. This is my network that I'm managing, and I'm doing a change inside of my own network. I shouldn't need the neighboring routers to support some new protocol, or get on the phone with the operator and have them schedule this event with me. So we're going to redesign the routers and not the protocols. And we do this through two new network management primitives: virtual router migration to break the routing software free from the physical device it's running on, and router grafting to break the links and sessions free from the routing software instance currently implemented. And so this will form two halves of the talk. So the first part is a project called VROOM, for Virtual Routers on the Move. This was presented at SIGCOM in 2008. So there's two notions of what a router is. There's this IP layer logical node in a topology, and then there's the physical equipment. In many people's minds, these are one and the same. That when you think of a router, you think of this physical box connected to other physical boxes to form a topology. And this causes a problem that if the physical router needs to go down, that causes the corresponding logical node to go down as well, which causes the whole network to have to deal with this change. So instead, what we'd like to be able to do is break this coupling and enable remapping the node, the logical node, to any physical node. So when this physical router needs to go down, we can remap the logical node, and there was no network-wide event. And so VROOM enables this remapping of logical to physical through virtual router migration. So an enabling technology here is, as the name suggests, is virtualization. And this isn't some far-off thing. This is routers are becoming virtual today. That Cisco and Juniper both support some notion of virtualization, not necessarily exactly as we need it, but they're moving in that direction. And this, what this means is that there's multiple control planes running simultaneously, and the data, each of them has their own view of what data plane they could configure, And then the line cards support this, where they have like multiple forwarding tables and things like that. So to see how this would work in the two examples, so the first case, planned maintenance. If you want to take down physical router A, you migrate the virtual router, shut down the physical router A, do whatever maintenance you need to, bring it back up, migrate it back, and you're good. You didn't have to reconfigure the router at all. You didn't have to deal with any network-wide convergence events. In terms of power savings, there's hundreds of millions of dollars per year spent on the electricity to run routers. So of course you'd like to be able to save a little bit. So the idea, as I mentioned, was to contract and expand the physical network according to the traffic volume. So you can see, when traffic is high, you can have a one-to-one mapping of physical router to virtual router, and then do a consolidation as a traffic demands. So there's some challenges to do this, of course. So the first is that we need to migrate an entire virtual router instance. So this includes all the control plane and data plane processes and state. The second is we need to minimize disruption. For the data plane on a 10 gigabit per second link, there's millions of packets per second being handled, and routers have many links, and these link speeds are getting faster and faster. So any kind of disruption on the data plane, if you have to take it down for any amount of time, that's going to cause a lot of packets. The control plane is less strict. That each of the routing protocols has some notion of retransmission, and the frequency of messages is a lot lower. And the third is link migration. We need, when I say that we're going to migrate a virtual router to a different physical router, for in this case, virtual router 2 from physical router B to C, there needs to be a link between A and C. And for this, we capitalize on advances in programmable transport networks, that when you see two routers drawn on a diagram with a line in between them, that's not actually just a wire. That in many cases it's this switched network that it goes through, this programmable transport network that will enable you to dynamically set up and tear down links between routers. And so that's where we take advantage of that. So shown here is the VROOM architecture. The first thing you note is the virtual router. So this is one unit of what's going to be migrated. Routers are designed such that the control plane and data plane are well separated. Many times the data plane is implemented in hardware. And we take advantage of this by inserting what we call the data plane hypervisor, which enables us to migrate between routers which have different data plane implementations. And finally, there's to decouple the virtual interfaces from the actual physical interfaces. We have the ability to dynamically bind that when you migrate the router to change which physical interfaces are being used. So now, recall that I said that the data plane and the control plane have different requirements. And so the key idea in the VROOM migration process is to separate the migration of the control from the migration of the data. And we do this through three steps. Migrate the control plane, clone the data plane, and migrate the links. So for control plane migration, we simply leverage virtual server migration techniques. Zen supports it, VMware supports it. More lightweight solutions, container-based operating systems like OpenVZ supports migration. And so we simply leverage them. And for the router, this will include the binaries, the configuration files, the running processes, and so forth. So to illustrate this, consider physical router A, and you're migrating the virtual router on it to physical router B. Traffic flows through it. You migrate the control plane, and traffic is still flowing through the old physical router. So the next step is to clone the data plane by repopulating. So what that means is the control plane would then populate the data plane on the new physical router. So we do this to enable traffic to be forwarded during the migration process. And it enables migration across different data points. So of course this whole process takes time. It can take tens of seconds. And the control plane still needs to be keep receiving those control messages, and the old data plane needs to be kept up to date. So we tunnel all the control messages from the old physical router to the new physical router, and then the control plane will update both the old and the new. And this is all done transparent to the control plane software. So at the end of this whole process, there's two physical routers which both have a data plane that has an identical table. And this simplifies link migration in that we can set up the links, migrate one direction of the traffic, migrate the other direction, and then tear down the links. So we built a prototype using Quagga and OpenVZ. OpenVZ is a container-based virtualization. So shown on the left is the old router, that's what you're migrating from, and on the right is the new router, which you're migrating to. So shown in each one of these boxes is a container. So this is one control plane, one control plane, and another control plane. To separate out the data plane from the control plane, we have this shadow D process, which taps all updates from Quagga to the routing forwarding table, and sends them down to a process called VRT, which is running in the root context, VE0. If you're more familiar with Zen, this is DOM0. And then it then writes it into the forwarding table. We support both Linux or the NetFPGA. Then we migrate over the container to the new router. At the end of the process, the VRT on the new router requests to Shadow D, makes a request to Shadow D to send it the entire forwarding table, which it does. And during this whole period, any kind of new updates that come down to VRT will be sent to both the old one and the new. So moving on to evaluation, there's a few things that are of interest: the performance of the individual migration steps, the impact on the data traffic, and the impact on the routing protocols. We did all the experiments on EmuLab. So we're not going to talk about the performance of the steps. That's simply OpenVZ territory. We didn't contribute anything there. For the impact on the data traffic, what we did is we set up various topologies. Shown here was the simplest one, the diamond topology. Migrated the router, and then migrated the links. We emulated the capability of the program transport network because we didn't have access to the equipment. But based on our tests, we didn't see any delay increase or packet loss. For the impact on the routing protocols, we set up this topology based on.
How can that be?
How can that be? Because
exactly the same topology. Okay, there's no extra node in there. Okay. I was thinking in the case where you take the one down.
Well, you wouldn't at this point. You're able to take N1 down. You have one redundant node. So before, when you would migrate it back,
So the traffic that is being routed out of N0, at what point does the routing table change? You only have one unique destination for traffic.
Yeah. So there's boxes in between these that kind of emulates the switching, and that's kind of like an instantaneous thing. So that the routing table on N0, which is a router, and the routing table on N3 don't have to change.
So something you do this once, or when you say, oh, there's no delay increase,
We did once,
do it
and
many times and see, sort of.
well, yeah, we reran the experiment many times, and we didn't see any loss in any of the experiments. So whether it was this one topology and we went back and forth, we did that, but in other topologies it was.
You're assuming you have sufficient capacity on the physical router to take the load.
Yeah, exactly. Exactly.
I was wondering how you're going to tie this into your power saving. If you've got to over provision the physical router to be able to run two instances of the virtual
Yeah, exactly.
How
You do need
How do I
the
net out on that? That's the,
yeah. So a virtual router has certain capabilities that needs to be handled, both control plane processing, CPU requirements, and data plane processing requirements. And when you migrate it to a new router, it needs to be able to support those requirements. So
What was the control plane protocol we used here?
So this in this case it didn't really matter. In the next case when it was
How did
BGP
you
and this.
transfer the virtual machine from N1 to N2? That was the control plane transfer that you did.
Yeah, so we're making an assumption that there's this out-of-band management network.
So you're assuming that there's some.
So perfect transfer control station.
Well, we if you read the paper, we did experiments where there is this dedicated management network and when there wasn't. And
So that's,
obviously
that's sort of validating the intranet setting, or do you, I mean, if these are
it was both. It was both.
But if these are BGP routers, how would that work? Suppose all of these are BGP.
Well, so N1 and N2 would be owned by the same ISP, so they would be in the same network. N0 and N3 might be in different ASs. So then the impact on the routing protocols, we set up the Abilene topology, not on the Abilene network, but on WINLAB. Slightly modified to make 2 Chicago nodes. And we did a migration event, or many migration events between the Chicago ones. And meanwhile, flapping nodes or links and so forth.
So, now to do power saving, you have to assume that there is a lot of redundancy in the network. At least there are a lot of redundant routers that can be shut down. If you look at this topology, how many redundant routers are there?
So this wasn't really testing power savings, but that was just one motivating
So
example.
my question is, in general, the network that ISP deployed, how much redundancy is there?
Well, it's not necessarily redundancy, it's provisioning for the peak. So in the peak case, there is no redundancy. Well, there's redundancy for fault tolerance, but it's not for for capacity. Well, there is over.
I think the point is that if your peak to value is right high, then you can save a lot of energy by shutting down.
Yeah, I agree to that, but the fact is, in order to do that, there should be you should be able to shut down one router and all the routes should have
So the assumption is you have multiple routes, how else will you increase capacity? Unless you have a knob for the link, where the link goes from.
So if you're looking for exact numbers, we don't have those. We didn't do the study. This is just a motivating example. What we're showing here in this evaluation is how the actual migration affects the routing protocols. So, to refresh that, we did the migration, and we did this, had BGP running in one test. We had OSPF running in another test. Same topology. The average control plane downtime, that's the actual time it takes to do migration of the virtual machine or the container, is 3.5 seconds. During this time, both the OSPF and the BGP adjacency stayed up. And there was at most one missed routing effort. To understand this, you can look at the various default values for the various timers. OSPF and BGP have some notion of retransmission. BGP is based on TCP. OSPF is, has this retransmission interval. Both of them have, some notion of sending some, periodic message saying, I'm still alive. OSPF is called the hello. BGP is called the keep alive. And you compare these values to the 3.5 seconds, and you see that roughly one will be missed. And for it to be called dead, you need to miss multiple ones. So to summarize VROOM, it's a simple abstraction that you configure a router as you do today, and you can just move it around. There's no modifications to the routing software other than the support for virtualization. There was no impact, in our test setup on the data traffic, and there was no visible impact on the routing protocols. So now moving on to router grafting, which is going to be presented at NSDI this year. So to take a step back, to recall what's the common best practice, the current best practice to move a link today. So we're going to want to move this red link down to the bottom right router. So you got to reconfigure the old router and remove the link. You got to configure the new router and add the link. And then that would cause a new BGP session to be established, and exchange a bunch of routes in between them. And this whole process takes minutes. So instead, what we'd like to be able to do is to view break this notion of this monolithic router and view it more in terms of its pieces. So in this case, we're talking BGP sessions, but grafting, as we'll talk or explore in the future, can have different ways to break up the router. So in here, what you would like to be able to do is break off the piece of the router that's handling this session, move it over to the other router, and just carry it on. So of course, this would be realized by the old router sending over some state, moving the link, and the new router being able to handle it. And so that's what router grafting does. It enables this breaking apart of router through splitting and merging. So this does require router software modifications. So in addition to the previous goals of being transparent and not having any disruption, we've got two additional goals. The first is that there should be minimal code changes. So in addition to making my life easier in the prototype, it would make the vendor's life easier as well. And and hopefully this would increase the likelihood of adoption. And the second goal is that it should be interoperable. Ideally between different vendors, like between a Cisco and a Juniper, but at a minimum between models and between versions. And this is, increases the usefulness of routing, as one of the examples did just this. But what this means is we can't, do stuff like memory copying or serializing and deserializing data structures. We need to export to a format that's independent of the implementation. So I'm not going to talk about the exact process, but talk about more of the individual pieces. So the challenge here is the various protocol layers that you got to deal with. So there's the physical link. So we're talking BGP here between the two routers. It uses IP to enable sending packets between the routers. TCP is used to create a reliable stream between the routers. And then there's finally BGP, which is the application that we're interested in, which enables exchanging routes between the routers. So go through each one of them from the bottom up. The link and the IP up first. So just as with the VROOM, the links are going to use the programmable transport network, which enable us to move or migrate links, physical links. And then for the IP address, as TCP requires, the remote endpoint would be sending to the same IP address. You need to either support a different version of TCP, which enables you to change IP addresses, but that would go against our goal of being transparent, that we don't want to have our neighboring routers change. So instead, we want to be able to keep the IP address. And the good thing is that, IP addresses are really only used for identification, and they're associated with the session endpoint, not necessarily the router as a whole. And in between routers, it's this layer 2 network, this optically switched thing, rather than being used in this IP address as actual reachability. And so we do move the IP address with the session. So for TCP, so to keep it completely transparent, what we're doing is we want to keep the current protocol as it is. So what we do is we bundle up all the state associated with TCP and just move it over to the new one and have the new one. Since it took over the IP address, it can carry on with it. For TCP, this includes stuff like the sequence numbers. It also includes the packet input queue, which is packets that you've received but haven't yet delivered to the application. and the packet output queue, which is packets that you've sent but haven't been acknowledged yet. Then you have to keep them around until they're acknowledged, in case you need to retransmit them. And now, finally, on to BGP, which is what we really care about. So, one of the key things to know here is that it's not just state transfer. So consider this made-up network. AS200, the one in the middle, is my network, and I want to migrate the link with AS100 to be done with this bottom. And so the way it's configured, going through AS300 and AS400 to this network is roughly equivalent. And so this top router would choose to go through AS300, this bottom router would choose to go through AS400, and their neighboring routers can choose either. In this case, it chose to go through 300. And that's what we told AS100, this router over here, that the path is 100, 200, 300. So now when you migrate this link right here to be done here, well, now the topology changed, this guy's decision changed, and AS100 has to be notified of the change. And there's various other changes that happen just like this. So it's not just state transfer. You need to rerun decision processes. So, of course, there is state that needs to be transferred. And, when you look at BGP implementations, there's, hundreds of thousands of lines of code to associate with it. So it's a little daunting task to think I'm going to go in there and every variable I'm going to export. But when you get down to it, what our goals are: data packets being delivered, routing adjacency staying up, and all messages being received. All you really need are two things: the configuration and the routing information. You don't need information about the state machine. You're either established or you're not established. If you're not established, well, it doesn't matter what stage of not established you are. Statistics are helpful for debugging, but not useful, or they're not used by the routing protocols. And then timers, just as timers are locally configured. They're not, there's kind of rules of thumbs that you have, but as we saw with the VROOM, that they're kind of loosely defined, that they're several seconds. So resetting them back to 0 doesn't necessarily affect the routing protocols. Now, of course, you could include all this state, but we're just showing that you don't necessarily need to. So the first piece of state is the configuration. So routers are configured by a command line, which is typically stored as a file, and it says information about the policies that you have, the details about the various papers, and then it's read into internal data structures. But we don't want those internal data structures. We want the implementation independent format, which is exactly what these command files are. So we extract the relevant commands and then apply them to the new router, and translating them if there's any differences, which there will be between vendors. Now, I'm not mentioning exactly what steps there are, but in the process. But there's going to be the old router and the new router both need to be configured for this to be able to happen. Now, you don't want the new router to be configured and then try to start establishing a BGP session or trying to send off routes or anything like that, or sending withdrawal messages. So instead, we modified the BGP state machine to add a state called inactive, which basically just means that it's waiting for the migration event to occur, to be migrated in. Now, for the route information, there's kind of two parts to it. There's routes you've learned from this neighbor, and then there's routes you've told to this neighbor. So when this neighboring router or this session sends you a route, in this case, router A. Router A will store it in its local data structure called the ribbon, run its decision process, and if it's the best route, propagate it to its neighbors. Now, when you migrate the link, B needs to know all of the routes that this neighboring router sent, because it needs to rerun its decision processes, and some of them, the routes that A didn't choose, B might choose. And so rather than having B request the neighboring router to resend all this information, which wouldn't be transparent. Instead, we have A send over all this information, and then B can rerun the decision processes. Now, for routes in the opposite direction, there's, routes, B and A might choose different best routes for a given prefix. In this case, B chose this black route, A chose a red route. A propagated it on to the neighbor over this BGP session. Now, when you migrate the link, it's B's best route that should be told to the neighboring router. Now, we could have, A withdraw everything and then B re-announce everything that it has. But in most cases, these are going to be very similar. So instead, what we do is we have A take all of the announcements that it sent to the neighbor, send it over to B, and and do a diff, and send only the diff. And in most cases, that's going to be a very, very small amount. So one special case that I wanted to mention was cluster routers. So routers today, again, are themselves big, large distributed systems where there's multiple rep processing blades that can handle various BGP sessions. So in this case, we show a very simple router that's connected to 4 neighbors. 2 of the sessions are terminated on the blade on the left. 2 of the sessions are terminated on the blade on the right. Each of them are running some router software, a BGP daemon or something. And there's some interprocessor or interblade communication. And for various reasons, you might want to move a session between blades. And why this is a special case is that the links are migrated internally. The switching fabric, any line card can reach any blade. So there's no kind of link migration, really. And the second part is that the topology doesn't change. So this router is still connected to A, B, C, and D. And since this router collectively acts as one router, even though it's across 2 blades, there's no need to rerun decision process. So we built a prototype, adding the grafting into Quagga. And we're currently working on doing it for Zorb. And in each case, the RIB and the decision process is well separated out in the code. We include this graph daemon, which would run alongside it. That's kind of coordinates the whole process. And we used a package called SOCMI for the TCP migration, which is just a kernel module that you can interact with it, bundle up all the state, send it up to the user space process. Evaluation is very similar to VROOM, impact on data traffic, impact on routing protocols, and then a new one, overhead on the rest of the network. Since your topology changed, and everybody needs to be updated. The impact on the data traffic is so similar that I won't even talk about it. Now, the impact on the routing protocols, there's 2 aspects. The first is the actual process of migration requires CPU cycles to do. You got to export it on one, transmit all that data, import it on the new router, which includes doing a lookup in the RIB, rerunning the decision process. So this whole process, which in our implementation, which we have optimizations in mind that we can do, takes 6.8 seconds. Between blades, 4.4 seconds, and this is for a large router cable. And the thing to note though is this isn't downtime. This is just kind of how long you might have a little extra CPU cycles being used, because this can all happen in the background. Now, the protocols are affected by the unresponsiveness. And this is the time from when you set the old router to inactive, you migrate the link over, migrate the TCP state over, and then set the new router to active. And this is only a few milliseconds. And that's the actual downtime. So now the overhead on the rest of the network, rather than giving some kind of quantitative data, we have some simulations, and we're currently working with the Tier 1 ISP to see how this would be in their network. But to get an intuition on what it would be is, it's really a function of how all the routers are configured and what the topology is. And if there's a lot of differences between routers, there might be more updates. So what we expect is that there's going to be, that there's going to be a kind of uniform policy across ISP's network. And you can optimize for the knowledge that you're migrating. You know that you're migrating from A to B. And so there's only going to be a minimal amount of communication needed. So to summarize router drafting, it enables moving a single link or session with minimal code change, no impact on the data traffic, no visible impact on the routing protocol adjacencies, and minimal overhead on the rest of the network. So now the last point to make is, are these two things complementary or can they work together? So, technically router grafting could do everything VROOM could do. You can migrate individual links independently, which is essentially the same thing as moving the entire router. But clearly, if you know you're going to move the entire thing, that's a lot more efficient. And but then there's also going to be times when you want to move just one link. And so I think that they're complementary. That in some cases you want one, in other cases you want another, and they can work together very well. VROOM didn't require any routing software change; it just needed the virtualization. Grafting didn't need virtualization, but it needed the routing software changes. So you can just run your grafting router inside the virtual machine, and it should be good. And each will be useful for different tasks. So in conclusion, to enable change without the disruption, we revisited the monolithic view of a router to decouple the software from the hardware. We presented VROOM to decouple the links from the router software. We presented router grafting. And as kind of ongoing work, we're looking at hosted virtual networks where you decouple the router, who runs the routing software from who owns and maintains the routing equipment. And that's the end. Thanks.